if you ask me if we're gonna, be able to make a dark matter teleport tomorrow once we figure out what it is, probably not. Maybe it could happen, but we will never break the boundaries of our knowledge if we don't go for the biggest unknowns that there are.
This is Lightbulb Moments by USC, a podcast that captures moments of brilliance across campus at the University of Southern California. I'm Jessica Peretta from University Communications. Today, we're talking with Vera Glusovic, Associate Professor of Physics and Astronomy at USC. Vera is at the forefront of cosmological research, and in today's episode, we dive into the mysteries of dark matter and the answers found in the cosmos. She discusses the excitement of uncovering the unknown, the role of AI in understanding the universe, and her experiences navigating a traditionally male-dominated field.
Why do you think learning about the nature of the universe and cosmology, and possibly also learning about dark matter, why do you think that it's so important to our everyday lives?
Because that's who we are, right? we're explorers. Like, if there's not a person that I've ever met who, who hasn't wondered about the night sky and the stars and the constellations. It's in us. It's definitely something that I think defines us as humans. And so if you ask me if we're gonna, be able to make a dark matter teleport tomorrow once we figure out what it is, probably not. Maybe it could happen, but we will never break the boundaries of our knowledge if we don't go for the biggest unknowns that there are. And this is exactly that kind of a quest, right? And like understanding what our universe is made out of, because it's not the stuff we know and understand in physics right now, is one of those things that's just like fundamentally pushing the boundaries of what we understand physical reality to be. And along the way, there might be some utility to it as well. We often, all the codes and algorithms that we're developing for that quest are often very useful in other domains of, industry and sciences and applicable sciences and so forth.
What aspects of your research really has been something that's been close to your heart and has excited you in, the overview of your career? What would you say?
So the kinds of questions that really drive me are, can we use, for example, observations of galaxies, which are these enormous structures of, so many stars and gas and so on, planets. Can we use those objects that we can see with our telescopes to then ask a question of, what is matter made out of? What are the particles that constitute matter? And you might think that, like, we do understand that. We have protons, electrons, and stuff like that. But the thing is that all of the things that we've ever interacted with here on Earth, so all of the matter that makes up us and life and planets, the air that we breathe, every single star in the night sky, all of that adds to something like 5% of all that there is in our universe. And in particular, 85% of matter is something we call dark matter, which is to say we don't know what it is. We know it's there. We can see its effects on galaxies. Galaxies are mostly made out of dark matter. So then that begs the question of, like, okay, so we've done pretty well over the history of physics to understand fundamental particles of matter that we experience on Earth. But our universe has a lot more. So what is this stuff? This is something that we can start to unpack by just looking at what the structure in our universe looks like and looking at it throughout cosmic history, which is what we can now do with observational surveys.
Could you tell us what is it that draws you? What do you really want to know about it?
So, the dream of physics is to hold, like in our minds, in our hands, on a piece of paper, in a computer, a full description of physical reality, right? What we're after are the laws of nature that underlie everything that we can experience in physical reality, right? So the quest to understand that 95% of the universe that's completely invisible as far as we can tell to us, but we can infer its presence through how it acts on the stuff that we can see on galaxies, stars, planets, and so forth. That quest is fundamental to completing that picture, to arriving at this like full understanding of physical reality. Now you can ask whether this is possible or not, and I would argue that every physicist has faith that it is, and it's just faith-based, because maybe we will at some point run out of things that we can discover, but I don't think we're there yet. There's a lot of data that we're collecting. This decade is going to be amazing in terms of astronomical observations.
And where do you believe, that the research is leading? What do you believe is the future with that?
Yeah, I think the signals will appear as anomalies in various data sets that are just not fitting within the present picture that we have. So I think what's critical for a community to do is to start putting the puzzle pieces together and understanding things like what does substructure in the Milky Way look like? What do those little galaxies that swirl around the center of the Milky Way, how many of them should we have? How heavy, how massive should they be? In a cosmology that features particular type of dark matter physics, while also understanding what does this universe actually look like when we zoom out? What will a survey of all the galaxies that we can see, the farthest ones that we can see, like for example from James Webb Space Telescope or JWST, how do those two very different types of observations come together under a particular theory? So I think unearthing these signals from dark matter microphysics, in other words, understanding the details of what these particles are, I think will require us to understand big data sets across the board and across scales. So I think this is where our field is starting to move, is towards away from, digging into the details of a particular data set and starting to put the various data sets together.
It kind of makes me imagine the discussion around AI and, implementing that.
I was trying to avoid going there.
I know. But, it's just such a popular topic that I feel like you can't help but think about how it's going to be implemented in every single field.
Yeah.
Yeah. And I don't know. Do you
Would
have
you like my take?
Sure.
Yes. I think we can't avoid it. So the part that I didn't go into is these data, especially on small scales that I was mentioning, are very complex. So it's really hard. It's becoming really hard to kind of lean into, the traditional way of approaching a discovery, where you see a set of data points and there's a bump and that's your signal from a new particle that we've discovered in an accelerator, for example. In cosmological data sets, I think the game's going to be much more like which theory fits all of the data that we have together better than any other theory. And this is something that we may not be able to make a plot that just shows a signal very clearly. We may be able to come up with heuristic explanations, but I think we are leaning more and more into analysis that are computationally heavy. And I think some of them will require various machine learning and artificial intelligence approaches. I think this has become a big trend in cosmological data analysis as well. And I don't think there's a way to escape it. I don't think we should. But I do think that there's an interesting philosophical question perhaps to ask, which is, what does discovery mean in the regime where AI helps us, right? What does that actually mean? If I can give you a simple picture like I did for how the universe evolves from different initial conditions to look very different if I change the physics of dark matter, that's me understanding the big picture, right? But what if I can't give you such a simple heuristic explanation of, how our universe comes together from all the underlying fundamental physics? And I think it's not guaranteed that these kinds of simple explanations can always arise. And I think AI will challenge us to find new ways and find, redefine what discoveries mean really in physics in the coming decade. I think it will be exciting.
How do you feel about the future of your work?
We're starting to see anomalies in various data sets, meaning like things that don't quite match up between different data sets. I think this is really exciting to look into because a mismatch just means that either we don't understand something about our data, which can happen, or we don't understand something about our universe, and we need a new theory to explain the observations that we're taking. And so there have been really interesting anomalies. For example, we've recently looked at one particular data set that seems to indicate that neutrino particles, which we know exist, we measure them, they're amongst the known particle components in the models of particle physics, but we know very little about them. They're kind of like ghosts. They go through matter. They don't interact very much. Every star produces them in abundance. They've been around since the Big Bang. But we don't know even their masses. They're so difficult to detect in laboratory experiments. Cosmological data recently have given us some indication to believe that they could actually be interacting with each other in the very early universe. So this is an example of, if this actually is confirmed, this is an example of new physics that we haven't been able to measure in a lab on Earth, but we can reconstruct by just understanding our universe a little bit better. So these kinds of mismatches, these little problems that don't quite fit together, are really exciting to look at if you're a cosmologist.
Is there a moment or a point in any of your work that you feel like you really felt that breakthrough moment, or that, that thing that made you so excited to really continue and say, oh, I think I'm onto something here?
I stick to these moments. These are small victories, but they make up life, right? Big discoveries come very rarely. There was a moment when I was starting at USC. I had put one of our undergrads, brilliant person, on one of the projects that I had come up with, and the problem was to understand what the measurements of the dwarf galaxies in the orbit around the Milky Way, what do they tell us about how dark matter interacts with normal matter? Can we use those observations to say something about those interactions? Problem was, at that point, we did not have cosmological simulations that would make the connection between the two. These simulations are difficult to run. They take a long time on supercomputers and so forth. And at that time, we didn't even have the code to do it in the right way. So we were trying to come up with the next best thing. And I remember the moment sitting and chatting with Kareem right here in this office when we realized we may not be able to model the evolution of galaxies precisely in this reality where these interactions exist. But what we can do is we can tell how much does how often does is a dark matter particle allowed to bump into protons in the first 2 weeks after the birth of the universe without disrupting what will become seeds of density that grow into galaxies later on. In other words, we figured out a way to say how much these interactions can smooth the universe and destroy every little galaxy that we see around the Milky Way today. And that didn't give us a discovery, but it gave us an upper bound on physics that superseded every lab experiment by a factor of 1,000. So this was a very powerful application of analytic theory, and it took us it was a very simple solution. At the end of the day, we did it in a very, very technically simple way, but it took a lot of conversation and a lot of pondering. And I remember the joy when we realized that, wait a minute, we can actually exclude all these theories, and have some room to spare, basically, compared to everything else that's been done up until that point. And this was incredibly satisfying.
Having this be such a important factor in your life, you spend so much time on it. What keeps you going?
So an aspect of it is definitely just understanding, just learning about the world that we live in. That I said before is just incredibly comforting to me. And there's a particular reason for that I want to maybe bring up again, and that is that, in a sense, we're really, tiny little humans on a tiny little planet in a vast universe that has all this stuff we don't understand. But at the same time, we have the tools to unpack it and really get to the bottom of it and hold it in our minds. And that's, I think, just really incredibly empowering. And then every day I get to share that with the students who carry the same awe for the universe. I get to talk to people who come here just to make a little dent in, in the vast unknown that there is in our universe. And we get to do it together. So all of it, the whole package, teaching included, I think is really what keeps me going.
What made you decide to go into this field specifically, cosmology, and particle astrophysics, if I'm not mistaken?
Okay. Yeah, correct. I often mention this movie that featured this wonderful person, astrophysicist woman who saved the world from an impact of a comet. It's very goofy and very, very cliche, but I think I saw it at a time when I was forming my self-perception. And so from that moment onwards, I think it never occurred to me that I couldn't do that. And so once you have a perception that you can be this person who studies this vastness of space, then that becomes comforting, because it becomes something that I can reach and hold in my mind, and understand deeply. So there's a sense of ownership in a special way of the reality that we live in. I think that's where the comfort comes from. But I never questioned if I can do it. And I really like bringing that up, because it's the visual art that touches on science can sometimes be really powerful in forming, even stereotypes in our minds. And this one was a positive one, right? Not every stereotype is a positive. So I was lucky in that way. And I recognize that now, especially when I interact with my students. And especially when my own confidence is challenged in a world that's, my field is dominated, is not very diverse, is dominated by men still to this day. And so there's many challenges that happen along the way. But this little something, this, initial condition, as we would say in physics, just changed the way that I could proceed through that world.
And how do you feel that you have been able to navigate, being in a field that is male dominated and feeling kind of those pressures and the outside pressures plus the internal pressure that you get from that situation?
Yeah, it's not easy. I think the key is doing exactly what I'm trying to do in my classroom now, which is to find a community and create a community that can remind you why you are where you are, and that you're worth, sticking around. But yeah, challenges are real. It is not easy to be in a minoritized category, and I'm recognizing that this is a challenge that a lot of people are dealing with in sciences, and this is something I'm passionate about, improving. Yeah.
And what would you tell, other women that want to go into this but are intimidated by that obstacle?
I would say that what matters at the end of the day is how much you enjoy what you do. And that's something like the decision about what that is cannot come externally. It only can come from like knowing who you are and what you enjoy. And so like identifying that early, like what is it? What is your passion? What is it that drives you? And then sticking to it and surrounding yourself with people who are going to be there when you're otherwise challenged in the world, which always happens to everybody, not just to women, but really to everybody. I think this is really, really important. So putting effort to build your own community, your friends who know you truly and who can support you when things are difficult is really, really important.
Amazing. Thank you so much.
Yeah, you're welcome. Thank you so much for having me.
Thank you for listening to Lightbulb Moments by USC. You can find this podcast on Spotify, Apple Music, or wherever else podcasts are found.